And in the last remark, we will observe that we will see a characterization of when A space is non-trivial by considering the equivalence of the divisors. Indeed, if we suppose that for a given divisor A, its associated A space is non-trivial, that means there exists a non-zero function inside of it. And by the definition of A space, that means A plus the principal divisor X is positive. And by setting A prime as A plus X, by the definition of the equivalence, we see that there exists a positive divisor which is equivalent to A. And for the other way around, if we suppose that if there's a positive divisor which is equivalent to A, so that means there exists a function X, non-zero function X in F, such that one can be written as a sum of the other one. So this, by the assumption, this is going to be positive, and this gives us that X is also, such an X is also in the function A space, is a function in the A space of L of A, so this is a non-trivial space. So it is quite also natural to consider what kind of A spaces do we have for some functions. For instance, if you consider the zero, it's quite natural to consider the A space of some spatial divisors like zero divisor. And in this lemma, we will see that the A space of the zero divisor is isomorphic to K. Actually, this is the same set as a base field. And if a positive, if a divisor is not positive or effective, its associated A space will be a trivial space. Possibly this is why this is called effective. And the partial order on the divisor set gives us informations about the subspaces of the given A spaces. And to see that the first statement, to prove the first statement, both are K spaces, so it's enough to see that one and the other includes to each other as a set. And for the right inclusion, by the definition of the A space, we know that zero inside of it. And for all non-zero constant, its principal divisor gives us zero divisor. So any constant is also L of O. And for left inclusion, if suppose that if you consider a function in the A space, that means it's the principal divisor will be positive. So in this case, if we write it as a sum of zero and the pole divisors, being positive means that there cannot be a non-zero term in the sum. So that means X has no poles at any P, because otherwise we can't get this inequality because of the minus term. So if a function doesn't have a pole, it should be a constant, because we know that non-zero constant has at least one zeros and poles. And we prove the second statement by contradiction. That means, let me suppose for a negative divisor, its corresponding A space is not trivial. So that means there exists a non-zero function. And by the definition of the A space, that means its principal divisor is bigger than or equal to minus A. And by the assumption A is negative, so the minus A should be positive. And in this case, X has only zeros, but has no poles. And this is also cannot be possible. This gives us contradiction, and hence the associated A space should be trivial. And to prove the first statement, first let me consider two divisors A and B is bigger than or equal, is less than or equal to B. And if you consider a function, it's enough to see set inclusion. So if you consider a function x in L of A, that means its principal divisor is bigger than or equal to minus A. And with respect to this partial order, we can see that indeed minus A is bigger than or equal to minus B. And this shows us indeed this function is in the also F space of B. And to understand, okay, we see that for the spatial divisors, what kind of vector spaces do we have concretely? We also want to see that when do we have isomorphism between two A spaces. And lemma 1.4.6 shows us if we have two equivalent divisors, indeed their corresponding associated A spaces are isomorphic as a vector space. And to see that, first let me suppose is equivalent to A prime, so that means there exists a non-zero function such that one can be written as a plus the principal divisor Z. So here our purpose is actually to see that one vector space contains the other one, actually contains the isomorphic copy of the other A space. And for this purpose, let me consider a map from the A space of A to function field F, which is defined the multiplication by Z, here Z, the function which appears in this equivalence. And we can easily check that this is K-linear and one-to-one because of the field structure. Please check. And since it is one-to-one, if you are able to see that image F lies in, so this is one-to-one, image F will be isomorphic to L of A, lies in the A space of A prime, we will see one inclusion. So that means our claim is that image phi lies in L of A prime, or equivalently for x in L of A, x times Z in L of A prime. And to see that it's enough to check the principal divisors x times Z, which can be written as a sum of the principal divisors of each one. And since x is a function in the A space, that means its principal divisor is bigger than or equal to minus A. And by regarding the equivalence of and A prime, in which we can see that the principal divisor of the product is bigger than or equal to divisor minus A prime. And this gives us desired. And for the other inclusion, if you consider the inverse function of phi, which is defined from the L space of A prime to function field F, by multiplying each function by Z inverse, which appears in the equivalence. Similarly, we can see that the L of A prime contains the isomorphic copy of L of A, and indeed it shows us two vector spaces are K isomorphic. Similarly, you can also check this inclusion. And finally, with respect to the observation we had in part 3 of lemma 1.4.7, since we have a vector space, we can consider the quotient space of two A spaces. And even though still we couldn't say something about the dimension of the A space, at least now we can see that the dimension of the quotient space L of B over L of A is finite dimensional, and its dimension is bounded above the difference of the degree of B and A. And to prove this lemma, actually we prove it by induction, because if A is less than or equal to B, without loss of generality, we may write the divisor B as the sum of A plus some places with positive coefficients. And here, as an inductive step, as a first step, we will prove this case. So that means our claim is that if B is equal to A plus P for some place P, dimension of the L of B quotient L of A is bounded below the difference of their degrees. So degree B equal to degree A plus degree P. So degree B minus degree A is degree P. And here recall that degree P is defined as the expansion degree of the residue class field over K. And if we are able to have K-linear map from this space into FP and with kernel L of A, we can complete the proof. For this purpose, first, let me choose to be able to define such a injection. First, let me choose a function with whose valuation is equal to valuation of B at P. And such a choice is always possible because V is onto. And with respect to T, let me define a map from the L space of B to the residue class of field of P by mapping the functions x to x times x, by mapping the functions to the evaluation of the product by T. The first thing, let me observe that this definition makes sense. So that means its image is not infinity, because if you consider a function from the A space of P by using the first item in the remark, we can see that VP of X indeed bigger than or equal to of minus VP of T. And by arranging this equation, indeed we can see that the product of xt has a positive valuation. It's P, hence xt in OP, so this image is not infinity. And we can also see that phi is k-linear by only applying the definition of a linear map. Please check. And finally, we can see that its kernel is the A space of A. And to see that, first let me consider a function in the kernel of this map. So being in the kernel, that this image will be identity of the residue class field. So that means X times P is a function in P. And if we use the correspondence between the places and discrete valuation maps, let me continue from here. We see that VP of X plus VP of T is strictly bigger than 0. Or equivalently, we can say that this is bigger than or equal to 1. And if we use the equality of the VP of T and the VP of B, and similarly, if you consider the equality of VP of B and VP of A plus 1, thanks to these two equations, we can indeed see that VP of X is bigger than or equal to VP of A. So this shows us X is also a function in L of A. And this proof works for general P. We can also see the other way around. And this shows us the kernel of A is L of A. And finally, by first isomorphism theorem, we can see that the quotient L of B of L of A lies in FP, and its dimension is bounded above the extension degree of the residue class field over K. So that means degree P, or the difference of their degrees. And to complete the proof, my suggestion to you to try to see that this proof in this works for the case when B is equal to A plus P1 plus P2 for distinct places. And maybe he may need to use the second isomorphism theorem here. And then you can complete the proof for the general case.